Hello and willkommen to the tank build video. It has been about a year in the making, but I'm very excited to finally share this video with you. At first, my thoughts for design were this: make something that is functional, that slightly resembles a tank, and something I will be able to 3D print.
Now this piece.
And so I created a shell of a tank that would just barely fit onto my 3D printer bed. I made models for the motors, camera, and electronic speed controllers I was using, and found models online for a Raspberry Pi and Arduino to get a visual approximation of how all the electronic components would fit in the tank when assembled. In this early model, I still had axles on the body because I thought I was going to be using wheels instead of the sliding plastic track. The electronics seem to have a good amount of space, which is important, as I have to account for the extra space taken up by wires, which are really hard to model but still exist in the physical tank. Next, I had to make sure I could get the major parts of the software to work, or else there would be no point in designing the entire tank if the software wasn't even going to work. Brace for impact. I'm actually going to explain my code instead of skip over it like everyone does nowadays. If you want to skip over this part by yourself, by all means do. Now that the software was working, we're also going to skip over the many iterations of wheels and tracks that were required to get the tank to where it is now, and start the assembly of the base of the tank. My original idea of using wheels had to change because after many tests, the wheel axles eventually all broke because of the constant stress of a load being applied at a perpendicular to the structurally weak plane, causing the layers to break apart. This is because of how the axles were 3D printed and several other factors. So this is how I had originally printed the side pieces of the tank, and you can see the structurally weak plane is the layers of the 3D printer, which is this way in this case, and you can see when you put the wheel on the side and apply a bit of pressure, yeah, that's not good. Also, on a side note, these are all of the failed 3D printed parts, this entire box full. Anyways, eventually I realized that PLA slides pretty well on PLA, so I took advantage of that and developed a kind of sliding mechanism for the tracks to replace the wheels. The track is still propelled in the same way as the original design, in the sense that there is a drive wheel which has a negative notch cut out of the track notch, and is propelled by a motor inside the tank. These tracks were designed and 3D printed in such a way that they require next to no work for me to get them to work, because I'm lazy and don't want to put over 100 axles together, because that takes time, effort, and additional materials. It was really nice and convenient to have tracks like these. It did, however, take many iterations in design to get these to work properly right off the print bed. Here I'm supergluing the side pieces onto the middle section of the tank, which holds the entire tank together. The string tensions the piece so that even the glue joints which don't fully encase the body plate of the tank are properly glued together. In other words, string help glue. And 1, 2, 3, boom! It's as easy as that, ladies and gentlemen. The beauties of editing and filmmaking. Now it's time to make the Canon assembly. Let's just start 3D printing some stuff. Now here we can see 4 of the Canon parts printing. We have the bottom, the middle, and the top piece. And we also have 4 other parts which I believe go somewhere within the Canon mechanism printing all at the same time. This is the top part of the Canon assembly, and in here we put our modified continuous rotation servo and put the cutout section of the BB feed disc on the servo arm. This only pulls in one BB at a time under the green protuberance, which is where the entry point is to the BB propulsion mechanism. One at a time, BBs are accelerated through a spiral in the middle 3D printed part by a notch on a rotating disc, which does such by maintaining a rotational speed, pushing the BB along the spiral. The BBs are dropped into the center of the spiral and are accelerated towards the outside edge of the spiral before they leave the cannon at inconsistent and only sometimes painful speeds.
And he doesn't have help.
That's my test subject. He's fine. Trust me. He's fine. Anyways, back to the build. This is the rotating BB loading mechanism. It can spin both directions at varying speeds. And here is the spiral part that goes underneath. And now I'm going to load some BBs to see if the hole lines up and the BBs fall through the center of the spiral. Now let's test the BB loading mechanism. Wait, why isn't it working? What is this? This good for nothing, useless garbage, you stupid piece of shit! There it is, well would you look at that, it works perfectly. First try, baby, let's go! And these are the electronics I'm going to be using for the Canon. Here we have a voltage regulator which turns the 12 volts from this battery into around 8 volts, which powers the electronic speed controller, which powers the motor. The electronic speed controller gets this PWM signal from this device here, which is powered from this battery. And there you have it.
And now,
it's Cannon Barrel printing time!
Okay, so now I'm attaching the cannon barrel to the middle section of the cannon assembly. There we go. This is disappointing, but let's put it together anyways. The entire assembly is held together by 3 plastic screws which are barely long enough to screw into the plastic nuts. Spinny thing still works, that's good. Alright, so now I'm going to rev up the propulsion disc and spin the servo with 1 BB in it once it's up to RPM. Oh god. Are you concerned about me firing plastic BBs all over the ground and polluting the ground with plastic? Don't worry, I bought these biodegradable BBs so that by the time I finish building this tank, I will have some soil, which I can use to cover up the plastic BBs. What's that saying? Out of sight, out of... I remember reading it once somewhere. There's also this thing called squeeze theorem, which I learned in my first year of engineering, and it goes something like this. If you squeeze it far enough into the ground, there's no problem anymore. I mean, it's not your problem anymore. If any of my math professors see this video, please know that was a joke. I know squeeze theorem actually has to do with juicing oranges. So over here we've got our electronics. We've got our Raspberry Pi, our Arduino, 2 motors, our 2 speed controllers for the motors. Then we've got 3 of these voltage regulators, which convert the 12 volts input from this into whatever voltage they need. Then here we've got another speed controller for the motor we have in this thing, the motor that shoots the BBs, and we've got a servo in the middle of that green part. And then connected to this Raspberry Pi, we've also got a camera up here. So basically the way these 2 devices talk to each other is through a serial connection, serial spelled with an S, which is provided by this blue USB cable. And basically for every frame that the Raspberry Pi processes, it sends the appropriate movement commands to the Arduino, which then outputs the appropriate PWM signal to the servos and electronic speed controllers. For now I'm going to be using one of these power supplies to simulate the 12 volts coming out of one of these 3-cell lithium polymer batteries. This one's a bit puffy, but that doesn't mean it's a bad battery. It means it's been on adventures. Alright, let's plug these in. Okay, so right now when not really anything is happening, the Arduino and Raspberry Pi are pulling around 0.41 amps. Right now I'm only controlling these 2 servos from the Arduino as a demonstration of the left and right drive motor PWM channels. So let's start up the program. So here you can see the left servo represents the left set of tracks and the right servo represents the right set of tracks. In this case, when the servo arms point down, it means that the track is off or has a low signal, and the higher or more counterclockwise the servo arms rotate, the higher the signal becomes, and the faster that set of tracks should drive. When my face is on the right side of the screen, the left tracks turn on. When my face is in the center of the screen, both tracks turn on and drive at a higher speed than the normal rotational speed, and when my face is on the left side of the screen, the right set of tracks turn on. This was the theory. In practice, it didn't actually work that well. Now for a quick intermission, let's check out these soldering skills. Alright, let's get a quick temperature check. Here you can see I'm pre-tinning both of the wires before I'm soldering them together. This is a great technique used by many professionals, and I'm clearly nailing it. Oh yeah, that's the stuff. That reminds me of the days when smoking was still healthy. Oh shit, watch out for the heat gun! You know, sometimes I even like to take some of this solder and just don't actually eat this. This is 60-40 solder, which means there's a 60% chance you die if you eat 40% of this.
That's true, don't Google it. Anyways, let's take a look at some more soldering skills. Here I'm using a wire stripper to remove the insulation from the wires so I can properly solder them together. Then I'm putting on some shrink wrap onto the wires so that I can cover up the solder joints once I'm done soldering them. This should prevent them from shorting. Do this first, always do this first. You have no idea how many times I've soldered together two wires without having put the shrink wrap on first. We're pre-tinning the red wire, we're pre-tinning the black wire, and boom, these solder joints are going to be so strong that professional arm wrestlers probably couldn't even tear them apart. I bet they couldn't even tear me apart, look at me!
Watch the heat gun, watch the heat gun.
Now we're testing motor 1 to see if it works. That's good. Motor 2. Works too.
So these are all of our electronics, and they're mostly fine. There's only one minor problem, and that is that the minimum speed of these motors is way too fast. For example, let me start them up real quick here. So just so you can see, this is the slowest that the motor can spin at. And as a demonstration of how fast this is, I'm going to put this identical gear on the motor and show you how fast it spins.
I think you get the idea. You can do the math if you want. Since the gear reduction I had initially planned would have made the tank way too fast, it would have probably pushed the limits of the facial detection program and the 3D printed tracks. The program would not be fast enough to respond to the zooming tank, and the tracks would probably break apart so fast you could discover the next big hose on if you had a microscope. So I decided to make the gearbox consist of a worm and a worm gear. I just modeled a gearbox up real quick to test it first before putting too much time into it, as this is a recurring theme with this project, doing a thesis on every single subsystem, trying to get it perfect, and spending my entire life on it. I got better things to do. Actually, no, not really. I don't really have anything better to do.
Beautiful. Now this piece has a lot of stringing. Let's get rid of all of that.
Yes, watching this back is making me a bit nervous, but that's fine. I think I still have all my fingers. Oh no. No. Never mind, false alarm, they're all still here, we're good. My finger was just bent over a bit. What a dumb joke. Anyways, back to me building the gearbox. Here's just some sped up footage of me cleaning up the stringy gearbox.
Let's see if everything fits together.
I tested the gearbox with a drill and decided that was an adequate first try of a gearbox, but eventually after more testing later on, the worm melted together with the worm gear.
Okay, so it has been about a year since I actually made the tank, and I managed to find the old gearbox. So here I can show you why I had to change the design. When I take this out, you can see this is the gear that was driven with the drill. And it's completely stuck here to the plastic. The two plastic pieces melted together, so they're basically one now.
It was time once again to go back into Fusion 360 and redesign the gearbox slightly to reduce friction on the axles by introducing bearings and to make general improvements. The problem of the friction between the gears could be fixed by printing the parts with a different, more heat-resistant or friction-resistant material, or by lubricating it. I decided to find a lubricant instead of use a different material because I didn't want to do material research and I didn't want to wait for new material to ship just to have it potentially not even work, let alone try to find the right 3D printer settings, yada yada yada. So off it was to find a lubricant. With a bit of research, I found out that a silicon-based lubricant is suggested for moving plastic parts, as it is supposed to not degrade the plastic. Disclaimer: every time I say degrees in the next couple of minutes, I'm talking about Celsius because I'm German and Canadian, and Celsius makes sense to both of those nationalities, and quite frankly makes sense to most people in the rest of the world as well. Silicon grease has a functional range of up to 1,649 degrees. Unfortunately, plastic only has a functional range of up to, let's see, the melting point of PLA is around 200 degrees, but the glass transition temperature, which is when the gears become useless and mushy, is much lower. It's around 60 degrees. So if we calculate 60 plus 1,649, then divided by 2, yeah, I definitely know what I'm doing. Water boils at 100 degrees and freezes at 0 degrees. Is this annoying you Americans? Calm down, it's just a joke. The imperial system, that is. Okay, it probably gets made fun of a lot. So on a metric scale from 1 to 10, how upset are you about it? Also, a quarter, an eighth, and 12 are not on the scale. Okay, I'm done now. Version 2 of the gearbox now has bearings on the sides that were previously plastic on plastic axles, and the mesh between worm and worm gear has received a liberal application of the silicone grease. A quick test shows half a week and $8 did not go completely to waste. Now it's time for the final assembly, the thing we've all been waiting for. Here I'm making room for the motor attached to the gearbox because in the original design, the motors were directly driving the wheel, and with the gearbox, some arrangements had to be made, and I was not about to reprint this entire body just so that I wouldn't have to cut this little part off with the Dremel. This was quite a thrilling moment, cutting through the plastic wall with the Dremel. Here I had to make a second cut because I like to live by the philosophy of measure twice and also cut twice, or 3 times. Really, however many times is required to make it work. The new gearbox now finally attached, let's see how it does. Now this is the type of performance I was expecting out of these tracks. Guess I gotta change the drive wheel once more. Now here's round 2 of greasing. Oh no, not these tracks too. Guess that drive wheel really does have to get modified again. This top plate of the tank was too large to print with my printer in one piece, so I had to ask a friend to print it for me. Here I'm taking off the support material, which is just extra material which is meant to help the 3D printer print overhangs, which this piece has quite a lot of. Finger check. We're good. Next I made the gear which should strafe the shooting mechanism left and right. Here I cut a piece off the servo arm and it flew into a spiderweb on the ceiling. What are the chances of that? Here we're gonna measure twice and cut... Cut twice also. This is exactly how I planned it. And now, friction fit this? Let's use some super glue instead. If you're tired of being able to move your fingers independently, feel free to superglue them together. Gear meet servo. Now on to the final test of all electronic subsystems before being shoved into the tank and hoping for the best.
So over here we've got the functional tracks and over here we've got the functional cannon mechanism that I will demonstrate right now by pressing this red button. Let's try that again with a close-up. Oh god. Now let's try this with the fully loaded ammunition storage. I hope this goes well. Oh god. Ah! Yes, it works.
This is now a full test. Alright, I just threw all the electronics into the Panzer and we should be ready to go.
Now this is the tank fully assembled. Let's take a look inside.
This is not a bomb. Trust me, I know it looks suspicious with all the wires and everything, but that's all it is. It's just a bunch of wires connecting all the electronics. Anyways, bye-bye, I have to go now. Now this is a nice looking tank. If you want to see the tank actually drive and see how it performs in the real world, go check out my other video that I made. This video is just to showcase how I built the tank. The other video actually shows it driving and stuff.
Oh my god.
Thank you for watching, and have a nice day.